Hey everybody, welcome, greetings, both of them. We're talking about circles today, and not just kind of the graphical representation of them, but an algebraic representation of circles, where just like we know the equation of a line is y equals mx plus b, or y minus k equals m parentheses x minus h if you like point slope form, or ax plus by equals c if you're a fan of standard form for the equation of a line. We're actually going to talk about an equation of a circle. So instead of just having a graphical representation of circles, we'll have many possible ways of interacting with them and everything like that. So the first thing I want to talk about before we hit circles, though, is talk about conic sections in general. And it's kind of an abstract idea. I mean, it's the name of this chapter, and you're kind of wondering, like, conic sections. It's kind of an unusual name. So let's talk about conic sections. I guess I'll briefly try to describe what they are. Conic sections are the graphs resulting from the cross section of a plane and two right cones, like ice cream cones. And that's probably not the most helpful. So what I mean by that is, let me draw a quick little sketch of what I'm describing. So a right cone, a right circular cone, all right, would look like this. And by right circular cone, it means that the peak vertex is actually directly above the center of the base, and it would form a right angle. All right, so that's a right circular cone. So imagine if I have two of them in this particular arrangement. All right, you don't have to be awesome at drawing necessarily, just get an idea of what's going on. So I've got two congruent right circular cones like that, and now imagine I go Fruit Ninja on this, and I actually like slice like across it, or diagonally, right, or vertically, and like all sorts of different slices that I could do. So if I slice across it, imagine that this is the plane that I sliced across it. It would result in cutting the circular cone, straight through it. And this shape is what I'm referring to. This is the cross section that I'm referring to. All right, now if this little sketch wasn't sufficient for you, I understand. And that's why I've got some additional technology that's going to help explain it. So here's a better sketch. Yay! So that actually didn't full screen the way I intended. So let me, I clearly misclicked there. I thought I grabbed it. So check this out. Here is my two right circular cones. I've got my yellow plane here is whooshing, slicing through it, and this is at a perspective drawing, so the shape resulting, the cross section from the top down view, in this case, is a perfect circle. So a circle is a type of conic section. All right, let's see, actually what can I do? Oh, I can do all sorts of stuff. So notice I can get different size circles if I slice at different locations on the right circular cones, right? And that's what I'm able to get, all right? Now, what do you think is going to happen if I change the angle of my slice? What if I go through this at an angle? What do you think that might do for this shape? Perfect. Wow, that's awesome. Watch. Oh, if I slice at an angle, let's see, maybe I can manipulate that a little bit better. I get not a circle, but an oval. Exactly. So if I slice at an angle, it's no longer circular. That shape mathematically is going to be referred to as an ellipse. and we'll be talking about those in the next section. And if I angle this even a little bit more, what if I was able to slice it at exactly an angle so that it's the angle formed by the edge of the cones? That's going to be my goal here. What kind of shape is that going to give me? Let's see. So I've got more ovals. I actually get a parabola. Let's see. Is it going to come back down here? Yeah, here it goes. If I slice it at exactly that location, I get a parabola. And that's kind of such an unusual outcome. And this is exactly the parabolas that you've seen before. All right, y equals x squared is perfectly represented by this sort of situation. All right, and all other types of parabolas. So we're actually going to later on talk about parabolas in a later section of this chapter as well. And what if I do a perfect vertical slice? Let's see if I can get this. Well, I actually get this interesting shape, and this is called a hyperbola. And you'd kind of be tempted to say that it's like two parabolas that are mirror images of each other, but these are actually not parabolic in shape. These are, in fact, they aren't getting steeper and steeper, faster and faster like a parabola does. These are actually getting less steep over time, and in fact, they are asymptotic. All right? This figure has diagonal asymptotes. And what do I mean by that? You guys might remember logarithmic or exponential graphs, how we had a graph that would get infinitely close to like the x-axis, right? Or infinitely close to the y-axis but never reach it. These, if you imagine some diagonal lines here, it would get infinitely close to them but never reach them. So this is actually on the extreme values of any particular quadrant of this graph. It's getting more and more linear, but yet it is still a curve. It's approaching a line and never getting there. So those are the four general conic sections. So you've got circles, ellipses, parabolas, and hyperbolas. All right. So that's the general idea for conic sections. All right. So, but today we're going to focus on circles. All right, good news. We're keeping it simple for today. Well, actually, we're going to actually have to know quite a bit today. Now, how would you describe a circle? Think of like a mathematical description for it. What do you think you could define a circle as? A never-ending line? Well, wouldn't a never-ending line? And how could you differentiate a circle different from an ellipse? Those are terrible shapes, but you know what I'm saying. Like, how could I distinguish a circle from an ellipse and not just like another curved object? You know, here's an infinite curve. Okay, and where is this radius starting from? From the middle. Exactly. A circle is defined as it's the set of all points all right, and this is just a math word. Anytime you talk about the set of all points, you could call that the locus of all points, not locust, all right, not like locusts and honey or plagues, right? Just a locus is a set of all points on a plane that are equidistant. Equidistant from a fixed point which is going to be the center. And what's the word you'd want to describe that distance as? What's the circle-y word that we use to describe that distance? What's the distance from the center to the radius? You'd used it earlier. So the radius is the distance from the center to any point on the circle. Right? So that's the idea of circle and radius, right? So let's see, I'll let you guys finish writing that down, and then I'm going to show you another Geometer Sketchpad sketch. This next sketch is brought to you by Algebra in Motion. All right, so this is not my own sketch. So it says a circle is the locus of all points in a plane of fixed distance, the radius, from a fixed point, the center. Okay, so here's my radius. You can alter what the radius is, right? Small circles, big circles, different things like that. Now, question, well actually let's do this first. So if I want all points that are this distance, imagine I've given these two constraints and I'm like, okay, now let's go out and draw all of those points. Let's see what that would look like. Let's collect this locus so you can see if I was to draw all of those points, right, it's a fixed distance. And this is almost doing what a compass tool does, right, where I'd set the spiky corner there and I'd have my pencil over here and I'd draw and I'd get a fixed distance from the center, and my resulting shape, I think you can see, is very circular. And in fact, right, you can see that that's the path that I'm getting there. So that is in fact my circle. Now question, what would happen if in my definition I didn't say that it was in a plane? What if I didn't restrict it to being in 2 dimensions? What would I get if I had the set of all points that were a fixed distance from the center but in 3 dimensions? What would those points look like? What sort of shape or solid would happen if I had all points? It'd be like a ball, exactly, right? So you can imagine like a basketball or a soccer ball, there's a center, right, which usually you can't access because it's contained within the ball. And all of the points that are equidistant from that center would give me a ball shape. The math word for that is sphere. Okay, so that's why the definition of a circle had to specify that it's in a plane. So it's the 2-dimensional version of that. I was restricting it to just 2 dimensions, not 3. Okay. Now, the primary factor at play here for the equation of a circle is distance, right? This fixed distance is what matters to us. So it turns out that the equation of a circle is going to be very much related to the distance formula. Okay? So let's actually talk about the distance formula. And in this case, I'm calling that distance my radius. So I would have that the radius is equal to the square root of, and I'd have 2 points. Well, let's see, my center, I'll have, let's see, my center I'll call the point h comma k. Okay? And I want a set distance from all of the, from the center. That set distance is the radius, and I want all possible other points, x comma y. So I'll just say other points would be any x comma y that makes this true, so x comma y, right? So what would that distance formula look like if I plugged it in? I'd get r as the distance, and then I'll plug in, I'll have x and y will be my x2, y2, I guess. And h and k will be my x1, y1. So let's just plug this into the distance formula. I'll have y, nope, I lied. I'll have x minus h squared plus y minus k squared. And in fact, they decided not to leave the equation of a circle in this form, but they modify it slightly. I guess they weren't a fan of square roots. So they were like, let's just get rid of this square root. And they do that by squaring both sides like so. And so the equation of a circle is r squared equals x minus h all squared plus y minus k all squared. And this is the equation of a circle with radius r, right? Radius r, and center hk, h comma k. So interesting results for sure. Interesting outcome. So let's see if we can put this to use, right? I mean, it's not your regular old y equals mx plus b. However, using it, you actually still can determine some valuable information from it. Just like in y equals mx plus b, looking at that, you would figure out m, the slope, and b, the y-intercept. If I look at an equation of a circle, hopefully you can determine what the center and the radius are. A-R-E-R. Classic, classic. So let's do an example of this. Example A. Let's see, write the equation of a circle with, let's say, radius 2 and center -1, let's say 3. There. So let's label what I know first. So I know that r is equal to 2. And I have my center is -1, 3, so that means h and k are going to be what? Yep, and k is 3, right? So now I'm just going to plug this in, and I want to point out that it's equal to r squared. And actually, usually I'll end up having the r squared on the right-hand side of the equation, but whatever. Whatever. So let's plug this in. So I'll have x minus h. So x minus -1. I'm going to show a little bit more work than I need to right now. Plus y minus k, so y minus 3 squared, right, equals r squared, 2 squared. So let's simplify this. This is the same as x plus 1 squared plus y minus 3 squared equals 4. And what I want to point out is that this and this, how do those relate to my original point for the center? Well, I just want to point out that those signs are the opposite of what you would have originally thought. All right, so vice versa, if I gave you the equation of a circle first, you'd have to realize that the center is -1 and +3. All right, in order to get that. And that the radius is not 4, it's the square root of that number. Okay, so let's actually, let's add this one more piece. Let's graph this equation. So to graph a circle, let me just go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'll draw the graph with you guys instead of just using my graphing software. All right, so that way you can appreciate my struggle amongst the people, right? So let's see. So to graph this, the center, according to the equation, is at -1, +3. So over 1, up 3 is my center, right? And the radius is 2, okay? So that means what I do to graph my circle, I actually go north, south, east, west. So I'm going to go up 2 from here, plot 1 point. I'm going to go down 2 from there, plot 1 point. Go east 2 from there, right 2, and left 2. And those are 4 points on my circle. Figuring out kind of some diagonal locations is usually a little bit more tricky because that'd be like over some square root amount and up some square root amount. So I then, to draw my circle, I don't draw it all in one swipe. I draw like one quadrant at a time. So I'll draw that, pick up my pen, draw that, pick up my pen, and then draw that. And behold, I've got a decent looking graph of a circle, right? Not bad. Not bad. So that's the idea, all right? That is the idea. So let's do another example. I'm going to have us graph the following. What if I gave you x minus 2 squared plus y plus 5 squared equals, and let's say 9. So what information can we pull from this equation? So just like y equals mx plus b, how you could read the m and the b from the equation, I'm interested in what is the center and the radius. So let's see, could someone tell me one of the coordinates of the center?
2.
So it's positive 2, and then the other one would be negative 5. Right? So I want to point out it's the opposite. All right, actually I'll even make that note right here. OPP, opposite. And if you are a fan of point slope form for the equation of a line, that's going to be something that you're going to be comfortable with anyway. The idea that it was always the opposite in that case as well. And what is the radius here?
3.
Right? It would be the square root of 9, which is 3. Okay? So then I could go about and graph this. So 2, negative 5. So it's going to be primarily in the fourth quadrant, I guess. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. All right? So something like that. So let's plot our center is over 2, down 5. And my radius is 3. So what am I going to do? I'm going to do my up 3, so 1, 2, 3, right there. So that's the point over 2, down 2. I just want to point that out. From the center, I'll go over 3 and land at 5, negative 5. All right. I'll go down 3. I'll land at 2, negative 8. Looks like I didn't go far enough on my tick marks. And I'll go left 3, which is going to land me at negative 1, negative 5. And then I can draw each respective portion. Now, one of the things I want to point out about conic sections is many of them, most of the time, will not actually be functions. All right? Definition of a function is for every input, there's exactly one output. And the problem here is that circles, if I asked you, what is y when x is equal to 2, you would actually have two answers. It'd be here and here, right? There's two values that make that true. Or when x is equal to 4, there's a point here and there's a point here. There's two outputs for the input. It also doesn't pass the vertical line test where those vertical lines hit more than one point. So I just want to point that out. They're not technically functions. Graphing calculators do have the ability to graph them, but it's not something you can do just like a y equals 2 thing. Although you can actually solve this for y, and you'll end up getting equals plus or minus some square root. So you could enter the positive square root and you'd get the top half of the circle. And if you enter the negative square root as a second equation, you'll get the bottom half of the circle, which is kind of interesting. So you can graph it. You might just have to graph it as two parts. And that's something that you can do. But yeah, so working with circles when they're in standard form is not that bad. Here, let me get a drink of water here. And then hold on to your seats. Actually, spend the next 10 seconds thinking about completing the square. Completing the square. So, all right. Actually, one thing I want to add, back up at our equation of a circle, this is called the standard form of the equation of a circle. Or standard form of a circle, the equation of a circle. And it turns out, just like with the equations of lines, where we had y equals mx plus b, and ax plus by equals c, and y minus, did they use h and k? I don't remember. Y minus k equals m parentheses x minus h. No, I think they, instead of hk, they use x1, y1, but whatever. We'll actually have two versions of the equation of a circle. All right? And it turns out general form, so general form and standard form. General form of a circle is not as helpful, sadly, but it is the following. It's x squared plus y squared plus dx plus ey, those are capital D and E, plus f equals 0. Although I have seen some texts will actually have the f have it equal the f, where they'll have the constant kind of on the other side of the equation. So there is that subtle variation here. And where basically D, E, and F, I guess I don't need the comma, are constants. All right, so those are just like any old numbers. And unfortunately, D, E, and F don't really represent the center or the radius or anything actually helpful at all for the circle. So general form, it can show up for different, different situations. We'll actually have a general form for all of our conic sections, and in comparing general form for the different conic sections, you'll actually have a decent kind of setup that you could compare them and figure out what kind of conic it is and all sorts of things like that. However, usually you want to convert from general form to standard form in order to graph it or to find out your center radius, blah, blah, blah. Now, one of the things I want to point out is that in general form for the equation of a circle, that notice the coefficients of my x squared and y squared term are both 1. All right? In fact, they will always be the same for the equation of a circle. They will be equivalent in sign and numeral. Okay? And I just want to point out that if I saw an equation like this, I would suspect that it was a circle because I see that there's both an x squared and a y squared term, which notice that in our standard form for the equation of a circle, we also would have, right, the x minus h all squared, if I expanded that out, would in fact still be, quadratic, right? And so would the y. So let's do a quick recall of completing the square, or solve by completing the square. No, maybe I'll just have us complete the square. I don't think we actually have to do a full solving. Actually, I changed my mind. Solve by completing the square, whatever. The language on that doesn't matter to me. Whatever, I'm a mathematician, not an magician. Englishician? Sure, whatever. So let's see, let's solve by completing the square. Suppose I have the following setup. What if I've got x squared plus 10x, and let's have minus 3 equals 0. All right, so here's an equation. It's a quadratic. I don't know how to solve this by factoring because, in fact, it is not factorable. There are no factors of 3 that subtract to be 10. It does not work. I could solve using the quadratic formula, the whole x equals the opposite of b plus or minus a square, that whole thing. That would work, but we're going to solve right now by completing the square. Completing the square was related to this perfect square trinomial. A squared plus 2ab plus b squared is equal to a minus b all squared. And the idea was, if I could make this look like that, I could then rewrite it as that. That's the general approach, okay? And so some of the steps to completing the square, step 1 was to move the old c term to the other side. So we'll add 3 to both sides because I don't want that anymore. And so I'll have x squared plus 10x blank equals 3 blank, all right? And then what I would do is I'd say, okay, what could I put here that would make it fit this pattern? I want it to complete the pattern. Does anyone remember how to do that? Well, I'll tell you guys. It's to find my new C term. Your new C was equal to b over 2 all squared. And it's actually related to the 2ab, all right, that I know that this is equal to 2ab, and that 10 in this case is the 2b part. So if I wanted to find my new C term, C is just whatever b is squared. And so that's why I take this, divide by 2 and square it. It's related to that, but whatever. So what is b over 2 all squared? Well, 10 over 2 squared is going to equal 5 squared equals 25. All right, so I'm going to add 25 here. And I can't just do it to one side of the equation. I got to do it to both. Am I right? I'm right. And now this left-hand side matches the pattern fully, in which a is equal to x and b is equal to the square root of 25, or 5. So I'm going to rewrite this pattern like this. Okay? It's factorable, and it's perfectly factorable according to a perfect square trinomial. So that is going to be rewritten as what all squared? Does anyone know? A minus b all squared, or a, actually that's a plus sign up there, sorry. Plus. And actually this pattern, if the middle term is negative, then this would be a negative, just so you know. So, thoughts? X plus 5 all squared, perfect, all right? Because a was the x, b was the 5. By the way, one way to find that 5, it's always the thing you had right before you squared it when you were finding your new C term. Right, so it's just b over 2, or it's the square root of this number. All right, and let's see, equals 25 plus 3, so that's 28. And now what I can do to solve, I don't want to FOIL this out or expand it. I actually can get rid of the square by root-rooting both sides, plus or minus, don't forget it. So I'll have x plus 5 equals plus or minus, square root of 28, I believe 4 is a perfect square that goes into that. And then I'll have, I could subtract 5 from both sides. And I'll get x equals negative 5 plus or minus, square root of 4 was 2, square root of 7. All right, so that was the idea of completing the square back in the days of probably some Algebra 2 or Math 3 equivalent course that you may have taken, okay? So hopefully that's vaguely familiar, because that's what we're going to have to do when dealing with equations of circles that are not in standard form off the get-go. So let's see if I've got enough time. Let's see. If I run out of time, guys, I'm going to actually keep teaching, and you guys will be dismissed at the regular time. All right, just so you know. What time do we get out, actually? Oh, okay, yeah. Oh, we're good. We're good. All right, we're definitely going to finish this. We're awesome. We're awesome. So let's see. Let's say I want to write this equation in standard form and graph it. All right. So we're going to have some problems on tonight's homework just like this. So suppose I've got this, 2x squared plus 2y squared minus 4x plus 12y minus 18 equals 0. Okay. Whoa, craziness. Crazy. So this is a general form for the equation of a circle, I assume. I suspect it's a circle because I've got a squared term for both x and y, and the coefficients of those terms are equal in every way, okay? Now, I want to rewrite this so that it looks like this guy, right? So notice this similarity to the right-hand side of my completing the square pattern. right? That's the same as that. So what I'm going to try to do is I want to complete the square for my x's and then be able to write it as a perfect square trinomial, the square of a binomial pattern, right? And I'm going to complete the square for the y's as well. So I'm actually going to do a double complete the square hook shot, nothing but net. It's going to be awesome. So here we go. Now the first thing I want to point out is these are 2's. Let's divide by that, no matter what. Whatever those are, I actually want to just divide everybody by that so that those are going to be positive 1's. And that actually was also the case back in the days of completing the square. The other thing I'm going to do, I'm actually going to bring my x's together as well. So negative 4x divided by 2 is negative 2x, and I'm going to have a blank there. And then my y's, so then that'll be plus y squared. And let's see, 12y divided by 2 is 6y, all right? And then I'll have a blank. And 18 over 2 is 9. I'm going to actually add that to the other side as well. Okay, so I also added 9 to both sides here, is what I ended up doing, okay? So notice the similarity in the concept, the setup here, right? I'm setting up this, but for 2 things, setting it up for x's and y's, all right? So I've got to complete the square for the x's. And by the way, if I'm going to add something here, I actually will also have to add it over there. And if I'm going to add something here, I'm also going to have to add it over there. Okay? So this is going to be interesante. So let's do this. What is my new c going to be for the x's? Well, I'll take the b, divide by 2, and square it. So that's a negative 1 squared. It's equal to positive 1. So I'll have plus 1 going here. But I can't just plus 1 willy-nilly. I've got an equation I'm dealing with. I've got to do the same thing on the other side, right? I've got to maintain equality. I've got to add the same thing to both sides of the scale to maintain balance, right? Keep the universe balanced here. And now let's see for the y's. Let's find its new c term, so to speak. So I'll take the 6, divide by 2, and square it. So that's 3 squared. It's equal to 9. So I'm going to add 9 here. And I can't just do it there. I've got to add it to the other side as well. All right. How are we on comfort level with this so far? All right. You see the general process. I've kind of brought the x's together, the y's together, and I've completed the square. All right. So now what I'm going to do is rewrite this as a perfect squared binomial, where it's going to be like the a minus b all squared thing, okay? That's what I'm going to do. And I'm going to do the same thing for this guy, all right? So let's see if I can do those. So what's the x is going to be rewritten as? What all squared? X minus 1. Yep. And for the y's, let's see, I've got a plus sign here, so plus. And for the y's, I'll have what all squared? Y plus 3. Okay, so it's not terrible. You just kind of have to know how to complete the square. And then let's see, 9 plus 1 is 10, plus 9 is 19. And hey, we're actually in standard form. We did it. So let's see if we can gather meaning from this. What is my center? Or actually, do you want to give me the radius first? Doesn't matter to me. Oh, good call. Even caught the negatives, right? Because it's the opposite of those numbers, right? Remember? Opposite, opposite. And what would r equal? So whatever the square root of 19 is, I don't know either. It doesn't matter, but it's exactly the square root of 19, so let's leave it at that. You could actually find a decimal approximation for the sake of graphing purposes. Square root of 19, let's see, that's a little bit bigger than the square root of 16, which is 4, but a lot less than the square root of 25, which is 5. So I don't know, I would guess maybe it's like 4.3. Let me see what a calculator says. square root of 19 is 4.358, so 4.36. Bam, there's an estimate of it. All right, but I found them. Hey, wonderful. So let's graph this. Let's see, over 1, down 3, and the radius is about 4, so over 1. I'll be mostly in my kind of negative quadrants for this. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Right? I'm realizing I'm going to go down 3 and then have to go down another 4 at one point, so that's why I decided to go down to 8. And let's see, I'll go over here, 1, 2, 3, 4, 5, and I don't have to go that high up here. I'll just go up to 3. So let's see if I can graph this. So over 1, down 3, right there. Okay? We got this, we got this. Let's see. So I want to go up about 4.36. So here's 3, I just went up. There's 4, and go up a little bit more. All right, so this distance is 4.36 that I just did, okay, roughly. I want to go over 4.36, so that's going to take me to 1 plus 4 is 5, actually, and then I actually have to go over a little bit more there, don't I? So maybe my tick mark should go out to 6 on this side. And then I'm going to go down 4.36, so 3, 4, 5, 6, 7, plus a little bit more. Right there. And I'm going to go left 4.36. So there's 1, 2, 3, 4, and a little bit more. All right. And now I can try to draw a circle as best I can. And clearly, that scale is messed up because these tick marks were wider than those ones. But, and I'm actually not as interested in your ability to draw a curve as I am in the locations of your points. All right, so make those nice and clear. Maybe even label them if you're worried about the legibility of your graph. Stuff like that would be good. Whew. Man, this has been a super long lesson, but circles, there's a lot going on with them. Thank you for sticking with it, watching this long. Well, thanks, internet friends. Have a great day.